Okay, we already done with the bipolar transistor. And now will be a second transistor. That's what we call a JFET. And the same thing, either bipolar NPN, PNP. They still get two things, two parts. One, first will be DC bias, okay? And the second one will be amplifier, okay? The JFET, therefore, Johnson field effect transistor is a type of FET that operates with a reverse bias PN Johnson that opposite to the bipolar transistor to control the current in a channel depending. Okay, let's see. Okay, first thing, okay, they can get either N channel or P channel. Okay, same thing like bipolar. You get NPN and PNP. In the JFET, they get one they call N channel, and the other one will be P channel. This is the N channel. Okay, they get the drain, the gate, and the source. And the arrow here point in N channel. On the P channel, the same thing. Only the arrow point out. Okay? And this is the physical here. This is the source here. The gate and the drain. Okay? And that will be N channel. And the second one, P channel. Same thing. Gate and source and the drain. Only the difference will be this is N channel and this will be P. Okay? That means one electron and one pole. Okay? DC bias. VDD provide a drain to the source voltage That's the VDD right here. Okay. And supply current from the drain to the source. That's easy to recognize. Okay. Amen. VGG. Okay. Set the reverse bias voltage between the gate and the source. Okay. This is the gate here. This is the source right here. The JFET is always operate with the gate source PN junction reverse bias. Okay. So basically, you can see the same bipolar, okay? They can get a VDD. They will be apply the voltage, okay, to the drain, and give given the current flowing from EDD to the drain, and that will be VGG. That's negative, positive, and the source connect to the route. Now, reverse bias of the gate source junction with a negative gate voltage produce a depletion region along PN junction, which it can into N channel and thus increase its resistance by restricting the channel width. Okay, now you can see they're showing you right here. This is the P side here. N side will be in the middle here. Okay? They're showing you when VGS more negative and the current will be this way. Okay? And now another one they're showing you. Now let VGG negative and the current going up. If you're looking into the display, there's a current flowing from the drain to the source. And now this is the channel is too small. So that let the electron moving. So that's why they let current. And the other one, you see that channel wider, okay? So more electron moving. So you get more current. And this is the JFET when you're working on the lab, okay? One will be a drain and a gate and the source. Okay, now let's see what's in here. Let VGG widen. Okay, the channel between the Y area. That's a channel right here. which decrease the resistance of the channel. That will be increase current ID. That means this channel will be wider and more current. Narrow will be less than current. Okay. The next thing, okay, we'll see that they're talking about the drain current. Okay. Now, this JFET connect to the route. Okay. And you get the current ID. Okay. And this will be VGS. That means from the gate to the source. And that one will be VGD, the gate to the drain. Okay. Now you're looking on the display. This stands for ID. The other one stands for VDS. Okay. And you can see the current will be keep moving, going up. Okay. Up to a certain point. Be here. That's what they call VP. VP means pick up voltage. That's only telling you when the current going up to the pick up voltage. Then now current will be constant, no changing anymore. Okay? And up to this point, that's what they're talking about, breakdown. Okay? So, basically, you can see from a 0 to the V peak here, this area, they call ohmic area. That means they can working like resistance. Okay? And from the V peak, point B to point C here, they call constant current. Okay? Area. And after that, that's breakpoint. We don't care about that. So VP ping off voltage. Okay? When the current reach to that ping off voltage, then now turn out they will be constant, no changing. Okay? That's what they call constant current area. Now, the maximum drain current out of the FET occur when the gate source voltage is 0. Okay? The maximum drain current ID out of the FET occur when gate to the source voltage is 0. You can see that the gate to the source voltage, they will be 0. Okay? The drain current is almost constant in the region between VP and VDS maximum. That's what they try to telling you. That means from this point B to the point C, the drain current will be constant. If the drain voltage is too high, the FET will be breakdown. Okay? That's not supposed to be happen. JFET act like current source when it operating along the almost horizontal part of the drain curve, okay, between VP and VDS maximum. We already explained to you. From that point to point C, B to C, current will be constant, okay? The minimum voltage of VP equal ping off voltage, okay? That means the minimum here, ping off voltage. The maximum voltage VDS max equal breakdown voltage, okay, between the ping off and breakdown. JFET act like current source with the value they call IDSS, okay? So that will be telling you from point B to point C that current they call IDSS, okay? IDSS stands for current from the drain to the source with sorted VGS equal 0. Okay? That means VGS equal 0. Okay? Then you can get maximum current, IDSS. And IDSS that made by the manufacturer. Okay? You cannot calculate it. When you buy the FED, they will let you know what the IDSS supposed to be. Okay? And the ohmic region, you know that is the ohmic region here. Okay? The most vertical part of the drain curve equal ohmic region that equivalent to the saturation region of the bipolar transistor. Cut-off voltage. Okay? The value of VGS that make ID approximately 0. That's what they call a cut-off voltage. Okay? So, remember, when they're talking about cut-off voltage, you have to understand. That means ID approach 0. Okay? That is for the VGS. JFET must be operate between VGS equal 0 and the VGS off. Okay? Comparison of the ping off and the cut off. VP is the value of VDS at which the drain current becomes constant and is always measured at VGS equal 0. That means current will be IDSS. VGS off and the VP always equal magnitude but opposite in the side. Okay? So basically VGS off and VP all the time will be equal. However, they must be opposite. Okay? So when they given to you VGS off, then you have to know VP. For example, if VGS off minus 4 volt and VP will be plus 4 volt, they equal, but they will be opposite. Data sheet, okay, usually will given either VGS off or VP, not both. Okay, manufacturer they can give you VGS off, or they can give you VP, but not both. The thing is you understand, they equal. Only thing is the difference will be opposite. One positive and one negative. Okay, now familiar with the drain characteristic curve. If you already know on the bipolar, that will be easy to understand on that one. This stands for ID. That for VDS. Okay. And you understand it is the IDSS. Okay. That's a current. IDSS. And at this point here, like the other one we showed you, point B, you going down. They will be given you VP equal 5 volt. Okay? That means when the current gets up to the point we already showed you in the past, point B, and the current now will be constant, no changing. However, that happen when VG, okay, VGS equal 0. So again, I try to make sure you understand this area of mixed region. That means the JFET will be working like the resistor. Okay. And this part here, they working a constant current. And that will be equal IDSS. Okay. Now, if we get a point A here, Q point, what the current, okay, ID equal, what the voltage, VGS equal. You go in here, see, right here, VGS equal -1. Okay, and the Q point here, okay, if you want to get ID, you go to the left. That will be ID. If you want VDS, you're going down. Okay? They're telling you. Okay, at VGS equal -1 voltage. Then you're able to get the ID current or VDS current. Okay? If you get another 1 point here, they will be -2 volt. Okay? And the current ID, you go to the left. Going down, you can get VDS. So, basically, on the JFET, there will be a voltage controller device. voltage controller. The thing is you change the VGS, you change the current ID, you change the VDS. Okay? So that JFET will be a voltage controller. However, in the past you learn bipolar transistor. Okay? Then in the bipolar, this will be the current, IB. Okay? So the bipolar will be current controller. Okay? That's the difference between the JFET and the bipolar. Okay? If you get a question, just let me know. Okay? The thing is sometimes you have to reading over. Hopefully you can get along with that. Now, add cutoff voltage. Okay. ID. You see ID right here. Equal 0. And VGS equal VGS off. You see, no channel here. No current can be flowed. That's why 0. Okay. So VGS equal VGS off. Okay. Now, the basic operation of PN. This is a PN. This arrow coming out, okay, is the same as an N-channel device, except that P channel requires negative VDD and positive VGS. If you're using the P channel, the voltage here have to be negative and the voltage here have to be positive. Last time I just showed you N-channel VDD positive, VGG negative. Okay? Now, example. For the JFET circuit show, they given VGS of minus 4 volt and the IDSS equal 12 milliamp. They want to know minimum volt value of VDD required to put the device in the constant current area of operation. Let's see what they try to do here. Solution. VGS of equal minus 4 volt. That's given. Automatically you know VP equal 4 volt. The minimum value of VDS for JFET to be in its constant current area. That means VDS equal VP 4 volt. You already know. This right here. Okay. They start going into the constant current at the point of VP. Okay. So they given you a VGS off, then you know VP 4 volt. So at the 4 volt VP, constant current with VGS equal 0. Make sure you understand. At this point here, VGS equal 0. Therefore, ID equal ID at S equal 12 milliamp. The drop across the drain resistor RD. Okay, that means the voltage drop across this RD here. Okay, VRD will be easy, right? They will be ID times RD. ID we already know, 12 milliamp. RD 560 ohm. So that's why you can get VRD equal 6.72 volt. Okay. Apply a Kirchhoff law around the drain circuitry. VDD. That means right here. They will be equal VDS. That means D here. S here. That will be the gate here. Okay, VDD supposed to be equal to VRD. Adding to VDS. Okay, you can see right here. Okay, VDS plus VRD 4 volt plus 6.72 volt, you get 10.7 volt. Okay. Now, JFET transfer characteristic curve for N channel. Okay. At this point here, if you want ID, you go to the right, they go here. Okay. ID equal 0. VGS will be VGS off. Okay. And if ID equal IDSS, that's telling you want VGS, you're going down. VGS equal 0. Okay. And this is the curve. Okay. Now see. For example here, when VGS equal 2 volt, minus 2 volt, that means equal right here. Then if you want to get the ID, you going up. When you hit into the curve, you going right. You get the ID. Okay. And the formula to calculate the ID here. ID equal IDSS times 1 minus VGS divide VGS off. That is the formula to calculate the ID. Okay. Now, for example, the Park-Zone data sheet of this JFET here. Okay. IDSS 9 milliamp. VGS off minus 8 volt. Using this value, determine the drain current ID. Okay. First thing, A equal VGS equal 0. So what the current ID? If you're looking in here, okay, VGS equal 0. Right here. What ID? You're looking up and you get IDSS. So VGS equal 0. Okay. ID equal IDSS 9 milliamp. Okay. Next, for VGS equal 1 volt minus 1 volt. Okay. Then you have to using this equation to calculate the ID. Okay. So basically IDSS is 9 milliamp. 1 minus VGS at minus 1 volt divided to the VGS of is that minus 8 volt. They calculated, they get current ID. Okay. Now, you can help me to working on that one. See here. VGS equal minus 4. What ID equal? Go ahead and calculate telling me what is the ID supposed to be. Using the formula ID equal IDSS times 1 minus VGS over VGS of square. Try to get along with this equation. Go ahead and try to substitute calculate it to let me know. See who can get it done. Anyone get answer, let me know.
$2.25 milliamps.
2.25. Who else?
That's what I got too.
So the formula IDSS mean 9 milliamp. Okay. Time minus VGS minus 4 minus 8. Where? Okay. Let's see. 4 divided to 8. 0.5 minus minus, that means plus 1. Okay. Minus 0.5, you get 0.5. Okay. Time 9. Answer will be 4.5.
Mr. Pham, excuse me, but don't you have to square this term? The one
Yeah.
minus,
Oh, sorry, sir. Okay. I forgot to square. Okay. That means 0.5 square. Okay. 0.25 times 9. 2.25. Thank you. Make sure they don't have too much formula. Okay. But this formula will be using all the time. Okay. So the answer right here. 2.25 milliamp. Okay. Any question on this part here? Okay, now try to see what else. The forward conductance, transfer conductance, GM. Now they're talking about another one. GM, transfer conductance, either change in the drain current for a given change in VGS. So by basic definition, GM equal I delta ID divide delta VGS. Okay. The unit of GM is Siemens. Datasheet normally give the value of GM at VGS equal 0. That means GM 0. That will be normally given, okay, from manufacturer. The GM can be calculated in the following. GM equal GM 0 times 1 minus VGS over VGS off. Okay, in case they not given GM 0, you can calculate GM 0 equal 2 times ID SS divided by absolute value of VGS off. Okay, so that is, you get another one. Okay, that's what they talking about, transfer conductance GM and GM 0. Okay, GM calculated by GM 0 times 1 minus VGS divide VGS off. Okay, and GM 0 normally they given to you for manufacture. If it's not, then you can calculate by GM 0 equal IDSS. Okay, divide to absolute value of VGS off. So now you get 3 formula to remember. First formula ID. ID equal IDSS times 1 minus VGS over VGS off square. And now GM equal GM 0 times 1 minus VGS over VGS off Okay, and if not given GM0, you can calculate GM0 equal to time IDSS divide VGS of absolute value. The thing is, they cannot be negative GM0. Okay, now see, the following information is include of the data sheet of the Fed typically IDSS they given to you. Okay, here. And VGS of minus 6 YM0 5,000 microsiemens. Using this value, determine A forward trend conductance GM for GS minus 4 volt. Okay, apply this formula. Can you calculate to me to see is it you get 1667 microsiemens? Go ahead and do. Make sure you're able to follow the formula. Make sure you have to working on, okay? So try to get along with the formula. The thing is when you're reading in the textbook, there's too many things you cannot follow it. You cannot understand. Okay? This we try to see what we need to make sure if you get through it, you can understand about the JFET. They don't have a too much formula. Okay? If whoever that get a first part 1667 microsecond assignment, sorry, let me know. Otherwise, next meeting, you get a quiz and you have to calculate anyway. They already given you the formula. Just substitute the value into the formula. Okay, who get it? So basically, they will be GM 0. Okay. Let's see. Right. 1,000. Micro. Siemens. Time 1. Minus VGS. Minus 4. Divide. VGS of minus 6. Okay. I get 1. Okay. 666 micro. Siemens. That's correct. One 667. Okay. Second one. Take one calculator ID at this point. So the formula ID equal ID at that. Time 1 minus VGS over VGS off. I want to know what VGS equal. What VGS equal. Right here. VGS equal minus 4. Okay. And VGS off minus 6. Okay, go ahead and calculate to telling me. Is it you get 333 microampere? Anyone do that calculation? Let's see. ID SS3 time 1 VGS minus 4 divide VGS of minus 6 square. Okay. They will be 0.333. Okay. Milliamp. And you converting to microamp. They will be 333 microamp. That's correct answer. Okay, so again, make sure you get the time. You try to redo it. Okay, you get along with the formula. And now, one example, they're telling you a JFET given IGSS minus, okay, 2 nano ampere for VGS 20 volt. They want to get the input resistance. Okay, this is the formula calculate the input resistance. Absolute value VGS divide IGSS given you 10,000 mega ohm. Okay, that's just a formula to calculate the input impedance. Okay, now we're talking about bias, DC bias. Many techniques can be used to bias the effect. In our case, the gate source junction is reverse bias, the most common bias technique. That means first one you get a fixed bias. Second one, cell bias. And the next one, voltage divider bias. We don't care about current source. Okay? 3 ways to calculate the DC bias for JFET. First one, fixed bias. Second one, cell bias. Okay? And the last one, voltage divider. Now, we'll see. Fixed bias or gate bias, the same thing. Okay? You can see that. This is the gate here. Gate bias or fixed bias, that's the same. Now they're talking about fixed bias. You see the circuitry here. They apply negative voltage. Okay, you get a VD. You get RD. Okay? And you get a resistor. That will be RG. Equal 1 mega ohm. Okay? This is the gate. This is the source. And this is the drain. Okay? First thing my question is, you get the V minus VGG. What V get equal? Who's telling me? If you're looking into the circuitry, I want to know what the V at the gate.
Should be the same as VGG because there's no current flowing, right?
Exactly. You understand. Okay? The thing is the resistor RG 1 mega ohm too big. That means no current can be flow. If no current can be flow, then the voltage at VGG and VGS gate will be the same. Okay. VG equal VGate. Reason A, no current flow from gate to VGG. Okay. And also, you know, by the basic definition, VGS equal, okay, VG minus VS. That's a very, very basic. VAB, that means VA minus VB. Okay, VGS means VG minus VS. Okay, so for the point B, okay, so how an AC signal is coupling to the gate of the JFET. Okay, you understand me? Without a GG here, okay, when you're working for AC, identical to the bipolar, when you turn circuitry to the AC, on of the DC voltage must be round. Okay, so why they need the resistor here? Okay, the thing is when you converting to the AC, then this will be round. Okay, if you don't have a resistor RGG here, that means your void here, AC signal, when they go up to this point, they going down to the round. So that's why they have to get RG so the signal can be go into the amplifier. Okay, that's why they explain to you. Okay, if RG omitted, okay, SO in the C here, no AC signal would appear at the gate because VGG is round for AC signal. I try to explain to you the reason they get the resistor RGG here. So when the VDC short to the ground, the signal able to go into the amplifier. Let's see what here. One of the most common way to bias the FET is with cell bias. Only a single power supply is used. Okay. The drain supply voltage VDD. However, this second one, bias, cell bias, they need graphic. Okay, you can see this is the cell bias. They only get only one power supply here. VDD. This no power. Okay. So, cell bias, they can say the power supply. However, In order to solve the problem, cell bias, you need a graphic. Basically, your guy don't have to. If you go into the university, then you have to do. That is the reason why you can open any textbook. You bought it, they don't apply with the graphic. Okay, we'll see what happened here. Another last one, voltage divider bias. You already learned bipolar. Okay, using the voltage divider, you can calculate the VG. Okay, and VG, Vs equal VG minus Vs. Okay, see, with the voltage divider bias, since the gate source junction has extremely high resistance, the R1 I not R2 voltage divider is practical unloaded. That means you can calculate the VG. Okay? Voltage divider bias is more stable than either gate or cell bias. However, same thing. They need the graphic. Okay, so summarize. Cell bias. Okay, we already did calculation. And next one will be cell bias. In order solving cell bias, you need the graphic, go with that. And the same. Voltage divider bias. You also need the graphic. I'm still talking about that for you, even you don't have to apply. Now, for this circuitry here, okay, that you're looking into the circuitry, you have to know, is it a fixed bias, cell bias, or voltage divider bias? Okay, before you can do calculation, if I'm looking on this circuitry, I know they will be fixed bias. The thing is they apply minus 2 volt here. Okay, for the circuit show, they want VGSQ, IDQ, VDS, VS, VD. Why they using Q? Again, if you're looking into here, right here, Q here, that means you can get any point Q. Okay, that's the one vary with the voltage. Okay, try to see. We can solve that one. First thing, we need to calculate the VGS. They given to you IDSS 5 milliamp, VGS of minus 4 volt. Okay. Then you using the formula VGS equal VG minus VS. VG here will be the same VGG. That means equal minus 2 volt. Okay. VGS equal VG minus VS. VG minus 2 volt. And VS is 0. So that will be given to you. Okay. VGS equal minus 2 volt. Okay. Now, if you want to calculate the ID, you have to using the formula IDSS times 1 minus VGS over VGS of remitting square. Okay? So, calculation, you get the answer here. And now, if you want to calculate the VD here, VD equal VDD minus ID times RD. That will get 9.25 volt. Okay? If you want to get the VDD, you take the difference. Okay? VDD and the voltage drop across RD. That given you. Okay? 9.25 volt. And also, another thing you must be memorized. All the time, ID and IS will be the same. Okay? Okay, any question about this example? First thing, I want to make sure you understand. When you're looking into the DC bias, you have to come up, either they will be fixed bias, or they will be a cell bias, or they will be a voltage divider bias before you want to solving the problem. Okay? Up to this point, you get any question, anything? The thing is that JFET are very, very important. You know, for your guy at work. The thing is later on they're using more JFET than bipolar transistor. Okay, now, if you're looking into the circuit, what type of bias? What type of the bias of the circuitry?
Self-biased, right?
What bias? You get fixed bias, cell bias, voltage divider bias.
Is it self-bias?
Perfect, cell bias. Okay? So last time, we already go through. Cell bias, they need the graphic. Okay? That means they have to give you this graphic right here. Okay? And you're using the graphic to solving the problem. For the JFET and the graphic shown for IDQ, VGSQ, and VD and VD at that. So basically you have to working on the graphic here. Now, let's see. VGS equal, remember for me, VG minus VS. Okay. VG right here, 0. Okay. That's the VG. Minus VS equal 0. Minus VS will be what? ID times RS. That means the current flowing here, ID, current in here, IS, and they already telling you all the time ID equal IS. Okay. So need to point A and B to draw the load line. Okay. They need the 2 point. One point on the current ID, another point on VDS, point A and point B. Then you can draw the line. Okay. Now they're telling you point A, set ID equal 0. Okay. ID equal 0, that means any point in here, ID equal 0. Okay. Then VGS equal 0. Okay. That means first one ID equal 0. This point here. Okay. This is the point here. At this point, ID equal 0. And also VGS equal 0. Okay. That means, let's see, point A, set ID 0. Okay. You can see the formula we calculate here. VG, VS, okay. They will be equal what? Minus ID. Times RS. Okay. So point A, okay, ID equal, okay, and this is VGS here. VGS negative and this side VGS positive. So you get another point here, point A. And now we need a point B. Point B, set ID equal any value. Okay. That means you can pick any point. Okay. That's what you can pick on ID. Okay. Select ID equal 10 milliamp. Then VGS equal minus 4.7 volt. Okay. So you get the 2 point A and B, you draw the line, and they will be intersect with the curve at this point. So at this point, you want to get the VGS, you're going down. If you want the ID, you go to the left. Okay? So basically, you can see this will be an ID here. Okay? On the graphic, they showing you how many volts. Okay? They given to you. Let's see. At this point, that's around 4.8 milliamp. And you want, okay? Let's see. VGS Q. Let's see, draw the line from AB. Intersection at the curve, E the point, and we can get value of IDQ and VGS Q. Okay? So you can get a point here, you go to the left, you get ID. Okay? Basically, you going down here, okay, you can get a VGS. VGS, that's a VGS right here. That means at the point 0 VGS here. So VGS, they show you, they equal minus 2.5. Okay? And VD, if you want to calculate the VD, you get the RD, you get the ID, VDD, ID, time, RD, VDS, VD, minus VS. Okay? So VS, when you get the current ID, you multiply by 470 ohm, you can get VS. Okay? VDS equals VD minus VS. But this calculation, you don't have to pay any attention. Okay? The thing is, they using for engineering. Okay? I just quickly go over here. Whoever can be follow it, that be fine. Otherwise, this is the voltage divider bias. And you know that will be VB, VS, VD. Okay? So, like the bipolar, same thing. Calculate the VB. Okay? You using voltage divider. Take 12 volt. VDD times R2 divide R1 plus R2. Okay? And VGS VG, okay? VGS VG minus ID times RS, okay? And let's see, VGS, okay? Basically, VG minus ID times RS, okay? VG equal, okay, 4.8 volt, okay? And you get the ID times R at 3.3K. This is the first equation here. To calculate the 2 points A and B to draw the load line, to get the point A, set ID 0. VGS equals 4.8 minus ID times 3.3. The thing is you set the ID 0, 4.8, okay? You get point B, set VGS equals 0, then 0 minus here, you get that point. Okay, now that's what they're talking about, that one here. Okay, for the voltage divider. Okay, so basically they need 2 points, 1 point here and 1 point here, and they draw the line intersection right at this point. You go to the right, you get ID. You go down, you get VGS. This is the one they try to get point A. How can they do? Okay. And also to get point B, how can they do? Okay. To get the point A, they say set ID equals 0. Then the formula VGS equals VG minus VS mean ID times 3.3K, okay, given to you 4.8 volt, okay, so okay, that means the first point 4.8 volt here. Now you get a second point B. Point B, set VGS 0. Then 0 equals 4.8 minus ID times 3.3K. Okay, so ID equals 4.8 divide 3.3, 1.4 milliamp. That means you get a second point here, 1.4 milliamp. You draw the line. They intersect with the curve at this point. You want ID go to the right. You want VGS going down. Okay? That means for voltage divider, you want to calculate the value you asking for a graphic. Okay? That's just an example, more example for cell bias and for voltage divider bias. Okay. Now, the last one I'm going to talking that for this circuitry, what type of the bias? What type of the bias here? You know what time bias?
It's a self-bias.
Perfect cell bias. You see around here, right? However, now they say, okay, I don't want any more graphic. So that's why they given to you right here. That means they given you ID equal 1 milliamp. Okay, see what they do calculation here. Given 1 milliamp ID, calculate the VGS Q, VDS, VD, VG, VS. First thing, VG, you know that will be 0 anyway. Okay? The thing is, this one is VG. VS, no, VD. Okay? So VG here equal 0, correct? VS equal ID times RS. Okay? The thing is we already telling you, this ID, this IS, all the time, ID will be same thing with IS. If you want VGS, you take ID times IS. VGS, VGS, VG minus VS. VG equal 0. VS you just calculate it. You get VGS. VD, they want to know VD. VD equal VDD minus ID times RD. Okay? So if you want to calculate the VD here, you take VDD minus the voltage drop across RD. Okay? And last thing, VDS, VD minus VS. You already get a VD. You already get a VS. That's why you can the calculation. So that bring it up for you one thing. They don't want to using the graphic. That means they have to given few things. Okay? Either in this case they given you ID equal 1 milliamp. Then you're able to do calculation. If they not given you ID and they have to given you something else. Okay? And that will be happen the same thing for bipolar. Now for the voltage divider bias. We don't want using graphic. So that's why they have to given you something. Okay? Okay? So basically, on this one here, okay, let's see. Graphically determined. No, We don't want graphic. That's a graphic. If you get a knowledge, you can see it. However, that's the last thing. Without the graphic for the voltage divider, they have to give it to you. VD. Okay, that's given to you here. And now you can calculate the VG, ID, VS, VGS, VDS. Okay, so if you get the voltage VDD, well, VD7, you can easily to calculate the ID. Okay, ID equal VDD minus VD divide RD. Okay, if you get the ID, and that means the same equal IS. And now if you want VS equal ID times RS. Okay. VG equal VG voltage divider, right? You take VDD times R2 divide R1 plus R2. Okay. So that's why. Then that IDS and that. They want VGS. VG minus VF. VG we already get it. VS we already calculated. And the last one, VDS, VD minus VS. Okay. After you get VD, they give it. And after calculate VS, you can calculate the VDS. So that will be telling you one thing. Very simple calculation. Okay. On the JFET, then the bipolar. Okay. So let's see. Okay. So next meeting, I will be given to you the problem related on of the DC bias for JFET at this meeting. However, we not apply for the graphic. Okay. I hope to try to go through it over. So you can do it. So any question to me? If you already almost done for the left bone, then we still get the JFET. You can working on JFET. Only the limited, we get only 3 more circuit board for the JFET. Okay. We are going to buy more, but that takes for a while. Okay. Any question? Anything? You want to be a technician. You really need, okay, to understand this is a very, very basic. We still get more time to go over, try to exercise. Okay. if you not get any question, okay, so we will stop it. Okay. Good night to everyone.
Hi, Mr. Pham. Thank you.
Thank you, teacher.
You're
Thank
welcome.
you.
Okay. Bye bye.
Bye, teacher. Thank you.
Uh-huh.